And working to get all our lectures on YouTube, and I actually have them up there right now, but I need to annotate them a little bit as to content because that got lost in the uploads process. But I was able to go to ITS's lecture repository and successfully secure them for the sake of uploading. Some people had asked about, in this course, had asked about sub-captions for those, and I am seeking to try to make sure that we can get them transcribed by YouTube's automatic transcription functionality. I believe that should be done now, but I need to double check that. It will be imperfect as that functionality is, but hopefully for those seeking to make use of the recordings as transcripts, that will give you something to go by. Okay, it's at least half decent for transcribing my English. I'm not sure what particular things throw it off. Perhaps it's occasionally my use of older English vocabulary. In any case, we'll try to make sure that those get to you on YouTube this afternoon. I have them all up there. I just need to go through and label them and so on. Okay? Any questions from folks regarding this afternoon's presentation? You okay to get some feedback on things? Yes? Oh. Okay. Sample size of 1. Better than 0. So that's a good start. Are there any questions that you want to bring to me right now before you finalize your plans for your presentation? Oh, I most certainly will be. I'll be here with the proverbial equivalent of a sharpened pen in hand. Not to jab you, but to record aspects of it that are needed for feedback. Really, that's the whole purpose of this. That's the whole purpose of presentations for the class. It's so that I can offer you some guidance with respect to your projects, and this will be a first chance to do that. So whether it's issues having to do with smoke testing for web-based systems, or whether it's issues having to do with plans for continuous integration support when you're using several different source code repositories or whatever, I'm glad to see what I can do to try to help. Okay? Any other questions? Okay. So today, ladies and gentlemen, we're going to be discussing a topic that was related to some materials that I sent since last time. It is materials related to the use of specifications within your software system. So you're going to be building up software systems, and I requested via email that you put in place specification mechanisms that describe what pieces of your system do in addition to actually implementing them. The idea is to have contracts that are defined that allow someone who's working on a different piece of the system, for example, or who wants to otherwise use your piece of the system on which you're working, to be able to know what it does at a high level, what job it performs, what requirements it has, what assumptions it makes, so that they, amongst other things, don't need to dig down into all details of the code, etc. So we're going to be talking today about this use of abstraction and achieving modularity and abstraction through the use of specifications with an eye towards testing, but also other QA processes. It'll be of direct help in putting in place assertions. It'll be of help in peer reviews. It'll be of help in terms of mocking for your systems. Be of help in terms of documentation. So this issue of specifications, those of you whose company, the pleasure of which I enjoyed during 214, will recognize some of these themes from 214. But they're one of the most important pieces of software engineering wisdom I can give for this course. And I'd like you to put them into place. With graduate students, my requests are stronger than that. I expect to see these mechanisms in place. Okay? So we're going to be talking about what these specifications are, give you some examples, and give you some sense about where they fit in. Now, the motivation for this lecture, as many of my lectures, is the challenge of complexity in the software space. Software is structurally and dynamically complex. It has many pieces moving at runtime, and they interact in ways that are not obvious to someone just encountering the software through its interface. There's lots of interconnections between pieces often. Maybe it's elements on the mobile device that need to talk to the server. Maybe it's elements of the user interface that need to be wired up together so they stay consistent. Maybe it's components from the database side that need to be exposed to the user interface. Lots of interconnections between pieces for it to do its work. And this complexity is a challenge. People in general are not that great at managing complexity. And when it comes to software development, this is definitely a pronounced feature. Complexity of software is a major barrier to effective delivery of value, and it leads to systems that are late over budget, substandard quality, that in short violate all three vertices of the what? Beautiful. Bang on, Warren. That's great. And this complexity has extensive impact on both sort of the human and the technical spheres. This is a really first-order issue. Grappling with a big code base is not, a big hairball of a code base is not fun. It's not uplifting. And often it's mind-numbing in terms of trying to figure out what's going on when you're debugging a problem or when you're trying to put in place new mechanisms. It's no fun for anyone, and it tends to be no fun for the client because it leads the client to encounter lots of bugs, and it leads the client to have issues in evolving their systems. So we've talked about the need in this class before, and indeed in 214, for modularity. So why don't we break systems up into pieces? Why, instead of one big hairball, do we want it to be composed of many, many small subpieces? Okay, usability is certainly, reusability is certainly a big part of it. We'd like to be able to take individual of those pieces and reuse them in other projects for other goals or in many different places within our system. So rather than repeating the same code ad nauseum at many places of our system, we'd like to write it once and use it many times. It's a key thing. Yes?
As a related concept, if you have everything sort of broken up into modules with contracts, you can completely change everything under the hood without breaking things as long as it fulfills.
And that's a key thing. Key thing about it. Is it Eric? Yes. So that's a key thing about what we're trying to achieve. Ladies and gentlemen, generally we prefer sanity in our software development. And if we change something at point A in the program, we'd like to be able to do so without having to change it, at countless other places, change countless other places in our program as well. We don't want the coupling to be so tight that all these different places have to be changed when we change one thing over here. That way lies madness, as Shakespeare said in King Lear. It leads to a huge amount of effort if tweaking something over here leads to the need to adjust things throughout the program. And so modularity allows us to encapsulate. It allows us to sort of parcel off pieces that not only can be reused from elsewhere, but where those pieces will be less coupled with these other areas. Not to say no coupling, but we'd like to be able to minimize that, and like to be able to minimize the gratuitous coupling, the needless coupling. So that's a great reason. There's many other reasons for this as well. I mean, one of the big ones is it allows a divide and conquer strategy. What do I mean by divide and conquer in this place, ladies and gentlemen? Riddle me that.
Your team up to work in parallel?
Yeah, exactly. So if you have a team composed of multiple people, you'd like to be able to proceed on the project, building the project in tandem at the same time, in parallel. And by delineating sub-pieces for it that are clear, have clear responsibilities attached to them, preferably clear contracts, you can do that. You can assign one person to work on one piece, one person to work on another piece, and they know enough about how the other pieces of the system will work through the contracts that they can put their piece into place without worrying about all the vagaries of these other areas of the program. So they can work on A, and they know how B and C work well enough through its contract that they can get that A can be put together. So modularity, by breaking things up, it allows efficiency, productivity, and it allows robustness. And this ends up ramifying across multiple areas of a system: co-creation, modification, testing, review, etc. So this is a central theme within software development, and it's also one that is increasingly critical as we build larger systems. So a key to modularity is this process that we call abstracting. It's building up pieces where we hide a lot of details of what's going on and expose the essentials, often expose the what is going on and less the how. We can recognize there's a large amount of commonality among different cases and create a single abstraction for those that's just parameterized according to things passed to it. But often what we're going to be focusing on that's called abstraction by parameterization. What we're going to be focusing on this lecture is this issue of abstraction by specification, hiding details behind an interface. Okay? Here we're separating an interface from an implementation. What do I mean by that? To separate an interface from an implementation. That's a lot of it, yeah. Very good, William. So the interface is the what. The interface tells me what I can count on, what it needs to do its job. And the implementation is the vagaries of the how it's actually accomplished. It's a little bit like the socket here on the wall. It's a little bit like that socket, or these interconnects up here, what have you. I don't need to know, and I don't want to know, frankly, all the details of where all these wires go after this. I don't need to know, is the first hop from this, the socket over there, or over here. Are these copper wires, or are they later type of vintage? What's their exact gauge? I don't want to have to know all of that. What I want to know is if I plug my my cord for my laptop into there, will it get a reliable source of voltage that's at a level that's spec'd out clearly? It's a standard interface that allows me to run my adapters on it. So it adheres to a certain standard. That's guaranteed. I can plug in with confidence. It'll be compatible with my adapter. And as far as how it's actually accomplished, as far as how it's realized, how it's implemented, they have the flexibility to do lots of stuff. As long as it reliably delivers the voltage at the rated levels of amperage and has appropriate grounding, etc. All the standard specs, if they adhere to that, and I can count on it, they're free to go off and implement it in any number of different ways. So here we're separating what's promised, the contract, from the implementation. It's kind of what we expect in real life, folks. If we go to a FedEx office and we say, look, we want to ship this package to Mississauga, there's going to be a set of standards for any FedEx office that we go to that's going to tell us you need to bring it in by 10 a.m. in the morning, and it will get there by 5 p.m. the next day if you do that. And that's what we expect. Any FedEx office we go to, we bring our package in, and we expect them to adhere to this contract, high-level contract. And it will be viewed as the most absurd and objectionable of aberrations. If we walked into a FedEx office and we say, okay, we want to ship the package, and they said, Fred isn't here today. Well, who's Fred? I mean, what do you mean? Say, well, he has flu today. What does this have to do with my package? And they said, well, Fred is our carrier and he's out sick. Look, I shouldn't have to worry about the vagaries of whether it's Fred or Sam or Sue that takes this package to the airport. I don't care if they bring it to Mississauga on a donkey cart, a fast donkey cart. But as long as they can get it there, I'm happy. We achieve less worries in life by being able to count on people delivering according to certain standards. So it's a separation of interface from implementation facilitates modularity. And here we're hiding details of implementation. We're making clear what we promise. And as far as how we do it, that's our business. As long as we know what people are counting on from us, and as long as they know, what things are guaranteed. Okay, so there's many benefits by this. Modifiability is one of the key things. Locality as well. The things that are sort of tightly coupled together in the code base, which is desirable. And reuse as well. We can abstract over mechanisms that differ in their details. We could substitute one in for another, and we can make use of one standardized implementation, implementation of a standardized interface in many places. If we create a better one, better mousetrap, we can go and place it in many different places. So, key motivator for this, suffice it to say, is the risk of change, and in this issue of modifiability is key. We often are driven by changes. We get driven by changes because of client requests. We get driven by changes because of issues having to do with technology evolution. A new version of Android comes out, and we need to update our systems accordingly. HTML5 is standardized, and we need to update our user interface for our website, etc. So this issue of evolution of our systems is typically a constant refrain in software development. And this abstraction can help us with that by separating interface from implementation. Okay, so let's talk about this a bit, and let's get a little bit more concrete. And let's get concrete about what I am seeking from you and what this has to do with your projects. Great stuff, apple pie type stuff. Let's see how it actually ramifies in concrete terms. So, this is an example I actually showed in 214 related to this, although in a somewhat different lecture contents. So, here we have a set of code that calls off to, that implements some bubble sort, and it's counting on ties being in the same order. And similarly, in another piece of the code, we have an implementation of bubble sort as well, and it's counting on this feature that ties are retained in the same order. And one of the issues here is, if we want to change things, if we want to change it to quicksort, for example, we have to do more work. Why? Because it's in two different places. We have to go and fix it here, we have to go and fix it there. And that's a pain. It's nice to not have to be able to not have to track those down. And ladies and gentlemen, in today's world, often it's increasingly hard to track down all the places where this is being used. When you have things like reflection and you have inversion of control and other mechanisms, it makes it hard to track down all sorts of examples of things. And it's often easy to kind of to miss some. So it's problematic. So, generally what we will try to do is to avoid that by having an abstraction in place, like sort abstraction. And we'll call it from multiple places, call this one thing. And then if we have to change it, we'll change it in a single place. Great. Great thing, great idea, modularity. That's nice. But there's a fly in the ointment here, folks, if we have a situation like this. And the fly in the ointment is that, we have we have uses of this abstraction, but we have certain things being counted on about this abstraction. Here, maybe this code after this call is counting on, when you sort these values, things that are in the same, that have the same value, they are retained in the same order between them. We're counting on that within our code, maybe implicitly. Maybe it's not even a conscious thing. And that could be an issue, because if we insert other sorts, like quicksort, for example, instead of bubble sort, we may end up having our code break. From the point of view of the person doing the sort, they're putting in place a more efficient sort. What can go wrong? What they don't realize is people could be counting on this feature that was guaranteed by bubble sort, which is now violated by sort, by this new quicksort. They're counting on this feature of things being in the same ties, and where in this code that uses sort. Now, maybe these were written by totally different people. Maybe this sort code was distributed by, vendor A, and this other code is written in the shop of vendor B. Vendor A doesn't know about every bit of code written against it. So they put in this change. They think, oh, our customers will be really excited by this, or our code base, the folks who use our code base will really like this. It'll perform much bigger on larger scale data sets, and suddenly code breaks. Now, why is it that these folks counted on this? Well, amongst other things, maybe they had access to this code base. Maybe this is an open source code base. They went and they looked at sort and say, oh, that's a bubble sort. I can go count on these things. I can go count on these things. And the folks who wrote sort have no idea. So the question is here, how do we make this code less brittle? How do we make it so that in changing A here, we don't have to change things everywhere else? Because that's the same situation here, just flipped around visually, right? We change sort, and now we have to go change these things which depend on it. And again, maybe it's by different people. Suddenly, you get an update to some library, and suddenly your code breaks. That's not very effective in terms of modularity. We can do a lot better than that. The key problem here is, how do we define this interface? How do the people who use this sort routine, how do they know what sort does? How do they know on what they could count in terms of sort's behavior? That, ladies and gentlemen, is really the question. So we're going to be talking in the next half hour or so about that issue. It's this issue of specifications. It's this issue of being able to clearly delineate what can be counted on within the code. Okay, so the basic issue here, folks, and I hate to tell students this because I wish it weren't so, but ladies and gentlemen, it is. The fact is that knowing the name or the signature of a given piece of functionality, like sort, is grossly insufficient to really understand what it does. If we could only count, if we count only on the signature of something remaining the same, we could be in a world of trouble, because how that's implemented, what it actually does, in fact, is not really spec'd out. The name gives a pale indication of what it does, but the signature by itself, the fact that it takes in a double star and returns an int star, it leaves a world of possibilities for what job it accomplishes. So we want some way of sort of knowing, some sort of way of knowing what this thing does. We don't want to have to look at the code. So let me ask this. Why don't we simply look at the code? Why isn't looking at the code the answer? After all, we live in a world of open source. Why don't we, okay, so we don't want this to break, we'll just go look at the code. Why isn't that the answer? Yeah, exactly. So it goes back to King Lear. That way lies madness. Folks, I mean, I like looking at code as much as you, although certain types of code. Maybe more. What can I say? I like looking at good code. And I'm highly disturbed to distraction by bad code. By code that is crufty and unseemly in its behavior. In any case, I won't wax lyrical about that. That will wait till a later time. But the folks, we don't have time to go look at implementations. We don't have time to go look at the implementation of every darn thing we're counting on. That's one reason. Give me another reason. Maybe the source code isn't available. How many of you have spent large amounts of time pouring through the implementation of object within Java? No? You mean that's not on your desktop? No. There's a huge amount of code that we're using these days, all the more so over time, that's simply not available to us. We're writing things atop of libraries, and increasingly the libraries are calling our components in an inversion of control type mechanism. Some of you may learn from me in 470. You know, where don't call us, we'll call you. The Hollywood principle, it's sometimes called. Our code gets called by other things. We can't see the source code for those. Source code evolves. But more than that, folks, even if we were to go look at the code now, who's to say that that code will not change? How do we know it won't change in a radical way? Okay, right now we're counting on this, and we know we go look at sort, and we say, oh, that's bubble sort. Oh, I can count on things that are ties being in the same order. But in general, that code could evolve. It's written by someone else. They have no obligation to adhere to every assumption we've made. They don't even know about our assumptions. So that's the problem, folks. It's not just we don't always have access. Even if we do have access, we may be counting on things that do not stay constant, that are not guaranteed. They didn't mean to guarantee. And in general, we don't have enough time. So that does not work. With all the open source code bases in the world, it's not going to help this. The question is, how do we define a contract of sorts that tells us what we can count on and that tells the implementers what things are being counted on by people who use this? Gives them the flexibility to innovate on other things besides the things that are promised, but know what things have to remain guaranteed. It's just like this wall outlet. They could come in here and totally rewire it. As long as I plug my thing in, they can do their business, I'll do mine. All right? So we're going to be looking at contracts, and contracts specified through specifications. Okay. So the idea here, folks, is that we'd like, besides better names like sorted indices, this is actually returning a set of indices which indicated the sort of origin of a sort. That's why I was returning an int star. We'd like to be able to have a specification, and this could run the gamut from informal to fairly formal, that indicates what is guaranteed by these things that are being called. So, for example, we start with a statement of purpose. So this routine sorts the content of values, the parameter, in ascending order, smallest to largest, returning an array. That was cut off. That was cut off. Okay, so there should be something more there. The precondition here is that the values passed is not equal to null, and the post condition specifies, in this case, the value of the return value. It returns this thing value, a thing that's specified for each sorted element, the index where that element originated within values. And values with equal elements with equal value retain their original order. Not very well specified, but that's what was planned. So if we go and we substitute in quicksort, we can do this as long as we guarantee that ties make the same property. We know that people may be counting on this property, that the order is maintained for equal elements, so we need to do the work when we evolve this to use quicksort to fix things up so that the ordering is retained there. And we could do that. It would take a little bit of work with quicksort, but we could modify it accordingly. So here, folks, we have a bit of a specification that tells us what this does, so that someone using it can just look at this and not look at all the code, and so that the people who do provide that implementation know what's being counted on. Does that make sense? That makes sense to people. We know what things are being counted on, what things are not, what guarantees are laid down, what things are still flexible. So what are the benefits of this? Well, this is like a recurrent question on pop quizzes and exams. What are the benefits of it? Well, to users of the abstraction, it specifies the guarantee. So they can count on things. So no need for guesswork, no need for access to the code base, no need to read the code. And very importantly, they can continue to count on these things. It's not just now. These contracts are typically contracts that evolve very slowly, if at all. So they're putting in place these guarantees, which, you know, even though the implementation may be evolved, those guarantees are still in place. Okay. Now, for creators of the abstraction, this is also freeing. It sounds like some work. I mean, you've got to spec out this thing. But the point is now, you know, you can, you know, for people who are creating this abstraction, they can write code against this interface before it's actually fully implemented. They can evolve it freely within the constraints of those promises. And they have knowledge of what features users could be counting on, which allows them to, for example, warn users or avoid, preferably, anything that would break users' code. So this is really quite desirable to be able to roll out a new library without the feeling that it will deliver negative value, because it will break lots of things. Has anyone here written code where a new version of a library comes out and your code stops working? Okay, it's happened to certainly me number of times, and it's happened to others as well. Sometimes it's a bug fix in that code base that's fixed, and it breaks your code because you're implicitly counting on it. But there's lots of other benefits too. Conceptual clarity. So often we're using something. It's a method. We think we know what it does, but it's not fully clear. And you know, a specification can help eliminate latent ambiguity there. And it can help draw our attention to certain exceptional or boundary conditions that we really didn't pay attention to. It can allow for easier understanding of the code, what it's doing, and clear documentation of sort of the requirements that are associated with it. It can also allow, when formalized, more aggressive optimization. And basically easier quality assurance. So I'd like to talk about that a bit. So one thing is, and this is where some of the benefits will come home to your groups. Okay, so you put these things into place for Prof. Osgood. Why is this going to confer benefits to you? It's going to take time. It's going to take time. How much time do you think it will take to put those things into place?
Less than a day.
Yeah, less than a day. It's not a day pumping out code, which is a lot of what fires some developers up. But it's a day in preventing yourself from pumping out bug fixes later. In terms of net cost, time-wise, it's pretty modest. And I would argue that these specifications are things you should be thinking through the elements that will go into that specification implicitly anyway when doing certain tasks. What are tasks that would make you think through, for example, what's required by a method, or would make you think through what it really guarantees, those sort of things? When will you be thinking those things through anyway? Unit testing. You're writing your unit tests. You're going to be thinking through, what does this method do? What does it do for these funky conditions? What is it counting on being the case in its preconditions? What does it guarantee in its post-conditions? You're going to be thinking these things through for that. Where else will you be thinking them through? If you don't document them, where else might you think those things through?
In the planning of classes and stuff, like in your
Yeah, the things that use them. So, maybe I can call that method here, but is it counting on already having entries to this thing I have to pass it? Is it okay if I pass it a hash table where it doesn't have any entries in it already, or what have you? These are things you're going to be thinking through there. Where else will you think them through? Where else will you put in place operational statements of your assumptions? In assertion. So you're writing assertions, you're going to be thinking these conditions through. Ladies and gentlemen, this is a matter of largely writing down things that are going through our heads. Writing them down so we can see them later and so that other people can see them. This does provide early opportunities for review of detailed design. If you put these things into place before you write the code, it allows people to say, oh, okay, so that's how your method works? Well, it needs to handle this other condition, or you need another method then because it obviously doesn't deal with initializing this element. You're requiring something here that's non-null, and initially it is going to be null. You need to broaden that. So, you know, before code is written, you can often do reviews here. You can directly derive many assertion checks. Given the statement of specifications, you can go directly to assertions. And, folks, I want to highlight this for you. With mocking, whether it's with Mockito or JMock or JSmock for JavaScript or what have you, you're going to be able to use these stated specifications to derive conditions for mocking. So, for example, if you have a mock, if you have an element that's mocked out, so maybe it's a mock of B. Maybe I'll draw it in a square. And you've got a mocked out version of B, but you have a spec of what B is counting on in terms of its methods and in terms of other features of the class, like history, properties, and variants we'll be talking about. Now we know what B is counting on. So if A is calling it, we can check, are those preconditions met? Is it passing us something that's within our view of what's legal? So for example, we can check, is the parameter that A is passing us to this method of B non-null? Does the array it's passing us have duplicate entries? Is it giving us a string that's not of zero length? These are all things we could check when we call a method in B. And they can be checked by mocking machinery, in many cases automatically, declaratively. You say, check these things. Checked. Secondly, we can help make sure that B is giving A something back that's sane, that makes sense to A in terms of the return values. If we have a spec for B, we know that, okay, it always returns a non-null quantity for this, so A may be counting on that. So when we have a mock for B, we'll return non-null quantities only. Does that make sense? Okay, so for mocking, ladies and gentlemen, these specifications will also be of great value. So specifications end up being one of these key technologies that can really allow a software project to scale to many people, to coordinate things effectively, to decouple people's work so they're not constantly poking you. How does this work? How does that work? Can it take something that's empty or what have you? And this will be one of the tools that will allow your projects to succeed. Now, I might also note that this really eases test case creation, not only for assertion checks, but creating the test cases before the code's in place, and less risk of violating this thing called the list scope substitution principle that we'll be talking about later in a later lecture. But basically involves the guarantees that a subtype makes, given that it can be passed around as if it were an instance of a supertype. It helps in the context of, what is that called? If you can pass around a subtype as an instance of a supertype, it's called, begins with a P, ends with an M. It's derived from Greek stock. Oh, man. Good. Morphism. Morphism. And what's the first word? Greek word for many? Poly. Polymorphism. You folks have heard that before? I hope. 270? Yeah? Okay. To do that safely, folks, you can screw your project over with polymorphism. Polymorphism is dangerous if you don't adhere to the list scope substitution principle. You can really end up in a bad way with very subtle bugs if you don't adhere to this. And we'll be talking about it. And guess what, folks? It counts on properties that can be nicely documented with specifications. to really do it justice, specifications will be your key. And you know, this ease of reasoning, this sort of clarity here, conceptual clarity, has practical implications. Lowers the risk of error, enhances speed of development, decouples people who can work independently, enhances the speed of debugging and testing, and you know, it can actually speed up performance in some cases because you know what can be counted on. Okay, so let's talk about these contracts. These sound good? How do we get there? Well, a contract defines an agreement between someone who's implemented something and someone who seeks to use it. It's a match between a demand and a resource. So here we have this agreement, and this agreement provides guarantees. It has requirements, and it provides guarantees in return. If you meet my requirements, if you bring that package in by 10 a.m., I'll guarantee it's in Mississauga by 5 p.m. It's a contingent thing. So contracts are described by specifications, and these can be implicit or explicit, formal or informal. I'm asking you folks to strongly consider, and I'm requiring of the graduate team that you put in place at least formal, explicit requirements, explicit contracts, okay? Now, there's several levels of these contracts, and I'll take a look at some of them on the formal side later. But this is what I want to see in your contracts. A statement of the high-level purpose of the method. What does it do? It computes the cubed root of the given argument to the specified degree of precision. It you know, sorts the incoming array and counts and returns the sorted array accordingly with duplicates eliminated. So describe the high-level purpose of this. What is it doing? This can be one sentence. This should be in Java docs if possible. Now, for methods, what I expect beyond this is preconditions, postconditions. Now, did you folks work with these in 270? So you've seen these sort of things before. Okay, so preconditions are requirements for the method to do its work. These are assumed to be the case by the method modulo assertions. Assertions will almost always check these things, explicit operationally check them. But these are things that this implementation is counting on. This given thing given to it is non-null, for example. That this array given to it is empty right now, and I'm going to insert elements into it. Yeah.
Some of those preconditions might be complicated enough that you can't test with a single assert statement, right?
Correct. Yeah.
Like this array has to be ordered.
That's right.
Have an assert that would automatically loop and find out that it's ordered.
It could actually. So that's a very good question, Kurt. So, how would you do that with an assert statement? So suppose you want to make sure that the array passed in is sorted, right? Because I want to use it. I want to use it for a binary search, something like that, right? How would you test that with an assert? Precisely. Yeah. You call off to a method, you know, I'm going to simplify things, you know, is sorted, right? Is monotonically increasing or what have you. You pass in the array. And this is actually a function. Now, this function is an element of your supporting infrastructure. It's actually, it may not be needed by the remainder of the program, but it's a part of your quality assurance. Much like parts of your quality assurance can be provided by mocking infrastructure or infrastructure used to hooks, like hooks for testability, etc. They'll insert errors. So to test your system's robustness to running out of memory, you don't actually have to run out of memory, or to make sure it will operate properly even under a disk error. You don't have to crush your disk, although that may seem fun to some people. You don't have to do that. Instead, you can just insert this error. There's often with programs, there's a fair bit of infrastructure. It's kind of like building a building. They have all that scaffolding up, all those forms up, and they pour the concrete in. So it is with software. And so this will be a piece of infrastructure that is sorted that you build for the sake of testing, but you can make use of it. And so then you'd make use of it in the cert statement. That's what I would do. And by giving it a nice name and having a nice specification for it, someone could look at that and say, I know what that does. Yes?
It's easy to conceive, though, a situation where the thing you're testing would take too long.
Indeed.
Right? So for testing, that might make sense, but there might be some asserts you won't have actually for preconditions.
Okay, but do remember, so those are good comments, but do remember what I said earlier about that notion of assertions being used, for example, to test brute force algorithms against naive algorithms. I give this example of a team from this class that had, they had a bus routing system, and they wanted to have they did some experiments, I think, with a brute force system, and it was slow. And so they said, we want to do a really quick system. We want to have a highly efficient. So they came up with this clever algorithm. And the problem is they played the game of logical brinksmanship a little bit too far, and their algorithm sometimes broke. And they could have put in place an assertion that the result of their clever algorithm equaled the result of the brute force algorithm. Now, you might say, whoa, now you've just slowed the system down. Why have the efficient algorithm if you're automatically running the brute force algorithm? And what did I say about that at the time? Does anyone remember? Yeah, so a lot of production code, and you can do this on a module-by-module basis, strips out asserts. In which case, this would only be tested during the development and testing environments. By the time it gets to the user, this is cut out. So I wouldn't use efficiency of testing things as the bed of Procrustes to chop off the legs of quality assurance for the sake of misbegotten goals of performance. The fact is, folks, if we have a system that's more robust, we can put the save time. If we can save time in debugging, save time on testing, save time in terms of quality assurance, save time in getting it to a stable state, often we'll have time left over that we can invest in the high-level performance issues, the high-level performance gains. And that's really the goal. Have any of you used Orbitz as a software, for airplane reservations? Any of you seen that site? Okay, what's that?
Similar sites.
Yeah. So Orbitz is an example of a company that a bunch of buddies of mine from grad school, actually, and they went off and founded the company. And it was a long shot, but they actually ended up succeeding incredibly well. And their original code base was written in what? Lisp. Which does not have the reputation for being the most speedy language. But the point is that if you can start with a robust, stable system, often that buys you time that you can invest in high-level optimization, which often pays off a lot more than low-level tinkering of code and getting things close to the metal in terms of performance. It's often the high-level algorithms that you use, spotting the hot spots in your program and focusing on them that lets you really gain big performance gains. And putting a lot of effort into making your system a little bit tighter by cutting corners and so on often ends up blowing up in your face because you end up having more bugs, etc. So don't go light on asserts for performance. If they're an issue, take them out of that module at runtime or take them out across your entire program. But the sooner that you can verify your program is solid in these regards and develop confidence, that the more you can put into bigger gain types of optimization. So, okay. So preconditions and postconditions for classes, though. I think this stuff is fairly routine for you. Then I'm going to go a bit lighter on some examples with that. Then, but have you seen this before? Invariance and history properties for classes. Okay. So this will be something that you want to take into account. we're going to be going through quite a lot of examples with this with Liskov substitution principle. So this is the deal, folks. For methods, I want to see preconditions, postconditions, because a method counts on certain things being the case when it's invoked, and it guarantees certain things when it finishes. This guarantee may be against return values and may be about changes it makes to the state of the system. The fact that it inserts something into a global symbol table, or that it updates something on the screen, or that it sends a message over the network. These things we call side effects. That's what postconditions guarantee. Now, for a class, we don't have typically preconditions specified per se. There may be one for the constructor of the class, to be sure. But for the class as a whole, for instances of it, instead what we're dealing with is other sorts of properties of them. So one of them is an invariant. It's something that's always the case for an instance of this class. Something that we can count on being the case. Maybe it's the fact that it includes no duplicates for the keys in it. Maybe it's the fact that it's non-empty, or that if you have a value, it's non-negative, or if you have if you're a collection that its length is greater than 0. These are properties. At any one time, you could verify these things, right? At any one time, you could check, is this empty? Is the length greater than 0? What have you. This is a property of that instance of the class that you can check at any one time. And this, too, is the fodder, the source of a lot of assertions. So, this can be the source of a lot of assertions in your code. You're just maintaining sanity checks. And a great thing to do is to have a method that you can call called isSane, or something along those lines. And you call it, and it returns a value that indicates, OK, is this instance of the class, does it match all these invariants? And by thinking about it, it sounds like a burden, but by thinking about it, you should be able to come up with some invariants. I'm not asking you, folks. I'm not asking you to come up with all possible invariants, but I'm asking you to put some serious thought into, what things could we check that would clue us into something that's really screwed up with these instances. I'm not asking for a complete formal demonstration of all possible properties. I'm asking for, good sanity checks that will confirm basic properties. So that's an invariant. That's something held true by a given instance at any one time. Mark my words. Any one time you should be able to check that. Make sense? You can check, is the length greater than 0? Is this non-empty? Does this have duplicated elements in it? Those can be checked right now. OK. The other thing, though, is history properties. These are properties that are somewhat more subtle, but let me. The idea is clear if you think about it. History properties cannot be checked at any one time. Instead, they relate to properties over time. So if we have an instance of this class at time 1, time A, and time B, where B is later than A, there may be properties that hold between this. An example would be that this class is immutable. What does that mean? Its Latin and Greek origins are swathed in mystery in my mind, so I can't tell you about its etymology. But what is, I believe it's Greek in its origin. So what would that mean if it's immutable? Cannot be changed. It's almost Platonic in its perfection. It doesn't have to change. This is actually an important type of object. Objects that are immutable simplify a lot of reasoning when we build software systems. Why? Why do they simplify our reasoning?
What's the difference between immutable and invariant?
An invariant is a property that is guaranteed to hold at any one time. Immutable is not something you can't check at this time, is this immutable? The way you talk about it is if time T1 and time T2, A and B, I said earlier, are they the same, then it's been immutable between, or it did not change between those times. So an invariant is something, it's a property that holds constant about the system But immutability is a property that has to do with sort of, it's not symplectic. It has to do with change over time. An invariant is a property that is guaranteed to hold on an ongoing basis. But you can't say it's immutable on an ongoing basis. That really, it just is. It is. Immutability is something about it, when you compare its value at this time and that time, it's a property involving different times. So immutability is one example of a history property. Let me give you some examples, some additional ones, that it's not decreasing in value. So you have a counter, and it's not going down in value. It either stays the same or it goes up. You can't check that at any one time, but if you have time 1, time A, and time B comes later than time A, the value at time B should be greater than or equal to the value at time A. A key present at an earlier time always remains present at a later time. You can't uninsert things into this. That's another history property. You're not deleting things in this. Once it's in there, it's in there. These are properties that are not about one point in time, but properties that sort of have to do with its behavior over time. Does that make sense? Okay. Now, these invariants and history properties often require a little bit more thinking than preconditions and postconditions, but they should be easy for you to spell out in at least a little bit of a way. And I'd love to see immutable classes. Immutable classes are often easily attained, and they simplify a lot of reasoning. We'll probably see that in a later lecture, but they basically mean you don't have to worry about side effects, which is a very important simplifying property of a system. So let's talk about this. Yeah, sure. Yeah.
When it comes to methods, what happens if you have a really inefficient way of finding an optimal solution, right?
Right.
So you opt for like an approximation method instead.
Sure.
Much faster,
Mm-hmm.
get very close to the optimal solution.
Yep.
How do you assert that? How do you go about asserting it? You can't compare it to the optimal solution.
Sure. Actually, you can, and we actually do that in many cases for certain types of algorithms. So if there's a brute force algorithm that you could use in testing it, and you want to make sure that it's within epsilon of the results of the brute force mechanism, you can actually assert that the value returned by the brute force algorithm minus the value returned by the efficient algorithm, the absolute value of that difference is less than epsilon, for example. And that's something which is indeed a recurrent feature of certain types of code. What it does require doing is in most cases, is writing that brute force algorithm. There are cases where we don't have to do that. Can anyone give me a case, for example? I even mentioned it, an example of this earlier in this lecture, where you actually don't need to write a complete brute force algorithm to test a property. Yeah. So, yeah, searching.
You can test searching easily without actually seeing it. You can test where it completes successfully without actually sorting yourself.
That's right. That's right. So you could. There's certain types of algorithms. They're not all by any means. They're probably not most, but they're an important subset where you could actually test the result for quality without the need to completely redo the procedure. So a search will be one example. You verify that you're searching for the certain string, and you got an index, which supposedly is where that string lives, and you look up, okay, is that string at that index? Yeah? Exactly. Yeah, that's right. So another example is, if you have a square root routine and you give it a value x, you should get out a value y such that what? Yeah, y squared minus x, the absolute value of that lies less than or equal to some epsilon, right? So we can actually test the goodness of this by comparing the result compared with the actual value we gave in and find that it's within some tolerance. So it's a good question, but there are important classes of algorithms so you can test these things. And I would say more than that, though, to broaden your folks' thinking about this. Don't get trapped in this notion of, well, you know, this works for toy examples like square root, but if you have a real system, you can't test that. The point, I mean, here what's really, what is the case here is that this is kind of a particular neat, tidy example. But the fact is there's a lot of cases where we perform real algorithms, and we expect the results to adhere to certain properties. For example, the result of this airline search for traveling between A and B, I've used this example before, you know, needs to return a set of legs that are, give me some properties that should hold about this.
The trip?
Okay, what's that?
You mean the trip?
Yeah, so, okay, so suppose I have some fancy, complicated algorithm that's going to route me based on all sorts of price constraints and time of day and seat availability and ticket type or what have you between city A and city B. What could I do to test that? I'm not saying to test that it's perfect. I'm not saying to test that it's optimal. But what could I do to basically test?
City A and city B should be the beginning and end of that.
Okay, it's a great start. And I'm not saying that facetiously. It's a great start. Because if your code were truly broken, you know, it might violate that, and you want to know that as soon as possible. So why not test that? Okay, give me another property it might be tested.
You could check to make sure that you will actually arrive at the airport before the connection leaves.
Good. That's another property that you'd expect this to adhere to which you'd expect this to adhere. How about another one?
The connection of cities is logical. If you go from city A to city B to city C, not suddenly from you suddenly hop at city C and miss the city somewhere.
That's exactly right. And incidentally, that was a property that all these properties, I think, that student system with the buses adhere to. So give me another one. Yeah.
You don't randomly decide to go somewhere and then come back.
That is exactly it. And that was the property. So Ryan, is it? Connor. Sorry. Connor. So that's exactly the property that their system violated. What it would have you do is, so it would say, okay, you want to go from Greystone Heights to the airport. Okay, you go to university, great. Get on bus to university, go downtown, great. And then get on this bus to downtown and get off the bus at downtown. So you had you sort of ascending the stairs, coming back down, ascending the stairs, coming back down. And then finally you got to the airport. It somehow got you correctly to the airport from that. But it had you looping on a bus, sort of, which is not a desirable property. So there shouldn't be loops in the graph where, you know, oh, we're coming into Saskatoon again. You know, that's right. It's Groundhog Day in the sky. No, you don't want that. So these are some examples of properties, folks, that we can check that could be described in postcondition, for example, for a method. Are they complete? Are they complete specification? No. But they're great properties that could be tested in assertions, in testing code, etc. And they can rule out large classes of bugs. Will they guarantee your program is perfectly correct? No. But they'll rule out a lot of bugs that could otherwise trip you up. Don't crucify your testing on the cross of saying it has to be perfect or we won't have any testing at all. That's not going to be helpful. Instead, you want to rule out large classes of problems by basic demonstration of properties that are guaranteed to hold. And so it is with specifications. Remember, these specifications are part of contracts. You're not promising all the details of what's there, but you're promising certain features that the user can count on. So I have a bunch of examples here that we don't have time to go through, but the fact that you folks have seen preconditions, postconditions before is encouraging to me. So here we might have a constructor. We test that as a precondition that something's not null, and as a postcondition, I'm not asking you to write in formal mathematic notation, but initializes this, the current object, to represent a set of conditions represented by the integers contained in elements. We have this method has, it has no precondition, returns true if and only if element of the set represented, etc. Now, I want to stress one or two things. One thing is, and this is an important property of these specifications, you can get a lot of gain out of making use of other methods. So, for example, in this definition of insert here, a